Hello everybody, my name is Fuhry and I work at Intel as a confidential computing solution architect. In this talk, Moritz Eckert from Edgeless Systems and I will explain how confidential computing can be used to easily protect an entire Kubernetes cluster. This protection holds even if you do not fully trust your cloud service provider or on-premise administrator. First, Intel's usual legal disclaimer. Now, a brief introduction of confidential computing. We've long understood that data should be encrypted when it's being stored, which we call data protection at rest. We also know that data should be encrypted when it's sent across the network, which we call data protection in flight. But what about when data is being actively processed? Even if the data is encrypted on disk or in the network, it gets decrypted before usage. As a result, the plaintext data is accessible in the main memory during processing. Besides, you do not know if the expected processing even took place. Confidential computing is the new protection frontier, mitigating these problems. It brings data protection in use and attestation. Protection in use means that the data is encrypted and integrity protected even at runtime. Data is encrypted in the main memory, it stays encrypted on the data bus, and it gets only decrypted inside of the CPU. Access controls inside the CPU make sure that only dedicated applications or virtual machines to which the data actually belongs have access to the data. With attestation, an application or virtual machine can mathematically prove three facts to an external party: that its code and data is as expected, that it is protected by a specific confidential computing hardware, and that this hardware is running with the latest security patch. Confidential computing can easily be combined with protection at rest and protection in flight. With this combination, end-to-end security for the processing and storage of sensitive data can be achieved. For us at Intel, it is very important that we provide all these security benefits at the best possible performance. Years ago, Intel basically created the confidential computing segment with our first technology called Intel Software Guard Extensions, or Intel SGX. Intel SGX draws the protection parameter very tightly around just the application. Today, it is widely deployed and used by hundreds of customers. Recently, we introduced an additional technology called Intel Trust Domain Extensions, or Intel TDX. Intel TDX draws the protection parameter around just the VM. As a result, it gets much easier to bring protection in use and attestation to existing workloads. In this context, a virtual machine that is protected by Intel TDX is called a trust domain, which we abbreviate with TD. Such a TD can contain a full operating system or just a minimal kernel. Besides, a TD can contain one application or multiple applications. Intel TDX's trust boundary around just an individual TD has several consequences. No software outside the TD has access to the code and data inside the TD. This includes the host OS, hypervisor, and firmware or BIOS. Additionally, a TD is also protected from all other TDs that might run on the same server. Furthermore, not even the sysadmin managing the TD can gain access. The CPU enforces this level of protection using multiple techniques. One main piece is that the main memory of every TD is encrypted with a different hardware-protected ephemeral key. Another important aspect is the newly introduced TDX module, which manages the TDs and is executed in a protected new CPU mode. This is just a quick introduction to how Intel TDX works. Let's now take a look at how our close partner Edgeless Systems uses Intel TDX to protect entire Kubernetes clusters.
Thank you, Benny. At Edgeless Systems, our goal is to bridge the gap and bring confidential computing technology like TDX into Kubernetes and the cloud-native world. Therefore, we built a confidential Kubernetes distribution called Constellation that lifts TDX into confidential Kubernetes clusters. These are completely isolated from the outside, but CNCF certified Kubernetes from the inside. That means no changes to the DevOps workflows of deploying, managing, or scaling your cluster. But for your workflows and data, however, that means everything is encrypted at rest, in transit, and now also in use. Thereby, Constellation allows our customers to be compliant, and it enables them to bring sensitive workloads to the cloud. It further enhances the state of Kubernetes security and protects application against powerful infrastructure-based threats such as cross-tenant or compromised cloud provider admin exploits. As Benny explained, TDX allows you to isolate entire VMs and encrypt them at runtime. That's also the building block of Constellation. We run the entire Kubernetes nodes inside such confidential VMs. That automatically runtime encrypts the nodes and all the containers deployed inside. However, for protecting an entire Kubernetes cluster from the infrastructure, that is simply not enough. For confidential Kubernetes, we need to make sure that also the control plane, the network, and storage are protected. And we need to make it verifiable, and we need to make it usable and integrate with the existing tools and workflows that are being used for Kubernetes today. Constellation, in that sense, is the first of its kind. It addresses these challenges by conceptually extending the confidential context from individual VMs to entire clusters, including the control plane and encrypting the data also in transit and at rest. The key aspect to understand how this works and the magic behind Constellation is the attestation and verifiability of TDX and entire Kubernetes clusters. And while Constellation is far more than that, for the sake of time, in this presentation, we will focus on the attestation and verifiability aspect. So our goal is to make entire Kubernetes clusters verifiable. That means we want a cryptographic proof that all our Kubernetes nodes are running encrypted within TDX. And we want proof of what exactly is running in those nodes from the firmware to the Kubernetes layer. With TDX, it works as follows. You can obtain an attestation report from the hardware about the state and identity of a confidential VM. That report is called TD quote. When we boot our confidential Kubernetes nodes, each component in the boot chain creates a measurement in the runtime measurement registers, short RTMRs of TDX. So first, the firmware is being measured by TDX itself when the VM is created. The firmware uses then direct Linux boot, where it directly measures and loads the kernel and initRD, which also includes the root hash of the integrity protected file system. All the Kubernetes components are then being protected by the verified file system. In the end, a Kubernetes node can be requested to provide the TD report from the CPU that can be verified against the ground truth of the expected RTMR values. Those values are being generated during the build time and can be linked to source code directly via reproducible builds. So in short, a Constellation node can be verified about its exact identity and integrity using the TDX remote attestation feature. Constellation uses that to verify entire Kubernetes clusters transitively. The first node in the cluster is being verified by the client, for example, a DevOps engineer who creates the cluster. During the initialization, a secure TLS connection is being established based on the TD report of the first node. If that verification succeeds, the first node will be provided with the desired configuration. It bootstraps the Kubernetes and deploys all the Constellation components. Finally, via that secure channel, it returns a kubeconfig for the client to access the Kubernetes API server. The same procedure is repeated for every scaling event of the cluster. However, not the DevOps engineers doing that process manually over and over again for every node. Instead, one of the Constellation components, the join service running inside every control plane node, takes care of this task. The join service verifies every new node, again based on the TD quote and a remote attestation procedure. Once verified, the new node is provided with the credentials to join the cluster. That way, Constellation can fully autonomously join nodes and scale securely, and the entire cluster can always be attested transitively. A lot more features we could nerd about, but in summary, Constellation provides fully verifiable, fully isolated Kubernetes clusters. So you can just go ahead with kubectl apply and your workloads are protected and isolated against the infrastructure. So now let's see this in action. Luckily, Constellation takes care of the heavy lifting and makes it easy for you to use. It comes with a simple CLI tool to create and manage Kubernetes clusters. It also provides tooling for Terraform, so you can include it into your infrastructure as code and GitOps pipelines. But for the demo, we'll just use the CLI. All right, so we're here now in our demo environment. I already have the Constellation CLI installed. On the left-hand side of this terminal, we will now go ahead and create, initialize, and start our Constellation cluster. We will then see how it protects against a very common attack. And finally, we will deploy a demo application to see everything in use. On the right-hand side, because it's a demo environment, I have a little pane of glass where I can peek inside and give you a bit more of the insights. So the first thing we'll do when we create a Constellation cluster is always to generate a config file. I will now go ahead and do this for our cluster here. All right, so now we have the config file. We can use that to create and provision the infrastructure. These are the confidential VMs protected by TDX that are our Kubernetes nodes. For that, we have the Constellation create command that expects us to tell it how many initial control plane nodes and worker nodes, in this case 1 and 2, should be provisioned for the cluster. So while this is running, I can set up my pane of glass. Let's see if there's already infrastructure for us. No, it takes a bit of time, so we can skip forward until the creation process has been completed. Okay, so now let's open the peek inside on the right-hand side here. And now I see the serial console output of our first control plane node. I will now go ahead and start the initialization of my cluster. That means the attestation process I've shown on the slides and the bootstrapping of the Kubernetes. This is being kicked off by using the Constellation init command. Again, init will take a bit of time, so while this is running, we will skip forward until it's done. While this is scrolling through, on the right-hand side, we can now see the logged runtime measurements that I've shown on the slides that are being generated by this CVM, by this Constellation node. And I will get back to them in a second. Okay, now the initialization has completed. We have verified the first node using our CLI, and the first node will then verify the other nodes based on the pattern I've shown on the slides. If I scroll up here, as I said, here we see the logged runtime measurements. And if I go into my configuration file and open that, there's a lot of information, but just ignore all of this, except the measurements part. Here's the expected measurements, the expected RTMRs for this cluster. And we can see that these match the ones on the right-hand side. It's just upper and lower case, but essentially it's the same. These values on the left-hand side here are produced by our build pipeline, and they are reproducible and verifiable by you, and the CLI will take them and verify the cluster based on them. We can now simulate a typical attack where somebody would exchange the firmware, for example, of your VM, place a backdoor inside, and to have access to your secrets. We can simulate this attack if we say, well, we changed the value here in our config file, which means we would expect a different kind of firmware, a different build of Constellation, where the firmware has this kind of measurement, and this is what we expect, and we verify the cluster based on this configuration here. And what we will see if we run the verify command that essentially reruns this attestation procedure. Let me run it real quick. It will go ahead, obtain a TD quote, and verify it based on the configuration file. It will say, well, here's an error. There's an untrusted value that we found at index 0, which is the one we changed from 5 to 6. So the attestation would fail. We will notice something is wrong, and we will not trust this cluster. Let me quickly change it back to the actual value here, to the 5. Okay, so this was, now that this showed how Constellation protects against these types of attacks. Now we will go to the other side, essentially the inside of Kubernetes here, where we have a CNCF verified Kubernetes that provides all of the features we expect. So we can just go ahead, deploy our application, scale it, observe it, all you would expect from a typical Kubernetes cluster. So let me set the kubeadm file so I use the right credentials to connect to the API server. And from there, I can now go ahead and deploy my demo application. I choose the emoji voting application from the Linkerd community, the Linkerd service mesh. That's just a fun little service mesh microservice application to demonstrate a Kubernetes deployment. So let me go ahead and apply from GitHub directly. Great, I will disable one of the services we don't need. And then let me show you what's being deployed. So inside this namespace, there are 3 microservices, 1 web front end, 2 backend services. They communicate over TCP. So because we deploy this in Constellation, everything is always encrypted. In runtime, because of TDX. In transit, because Constellation transparently also encrypts in transit. It doesn't use persistent storage, so there's nothing that needs to be protected at rest. But if it would, Constellation would automatically protect that as well. So now let's quickly wait until this application is up and running. It is, so we can see how it looks in action by exposing the front end to our local system here and open that in a browser window. Let me expose it. And now I will switch to the browser and connect to the web front end. And this is just a fun little toy application. Takes a short bit of time of loading. Here it is, where we can vote for our favorite emoji. For example, the nerd one. We the leaderboard, and we can be sure that our votes have never been safer than with this deployment. Let's go back to the terminal. What we've seen, we've created and initialized a Kubernetes and also a Constellation cluster. We've seen how easy it is to use the CLI, how Constellation protects against certain types of attacks, and we finally just used the Kubernetes as we would always do and deployed a fun little demo application. All right, that's it for the demo. In summary, we saw how Constellation lifts Intel TDX into the confidential Kubernetes clusters to protect your workloads and data from infrastructure-based threats. If you want to learn more about it or want to try it right away, check it out. It's open source. You can find it on GitHub, and you can set up your first confidential cluster in minutes. If you have any questions, please feel free to reach out to Benny and me. That's it. Thank you very much for your attention.